Good afternoon. My name's Jon Ball. I am the Chief Geotechnical Engineer for Bullivant. I started getting involved in piling in the last century, so been doing this game quite a while. Currently, I'm the convener for Eurocode 7 on piling, and just given up my post as technical lead for the FPS's technical committee. So that's all about me. So now, if I can, I'll tell you a little bit about our organisation and what we're going to cover today. So first of all, I'll go into our business, what we do, what we can offer, how we came across CHD as a technique and how we've employed it, what the differences is between, between CFA and CHD, some history, because a lot of people don't realise that it's quite a mature technique now. Give you some examples at the end, and then fly my own flag, just some of the scientific basis on which the technique has been developed over the years. So lots of numbers there really, but the point to make is that we produce about 1 million meters of precast pile every year. We manufacture them in our own plant. We have over 50 rigs, and we probably have a split of about 60% on the residential side, 40% on commercial side, and we use low carbon concrete as much as we possibly can, as much as the ground conditions will allow us to do. We've got about 500 employees based in 6 area offices around the country. And there's experts in each field in each one of those, and I look after the design side and the research and development side of that business at the moment. So in terms of techniques that we do, we have 4 main streams. What I would call as large diameter piling, although it's relatively small in the scheme of things in the industry as a whole. We do ground improvements, we do systems where we've got precast beams that we incorporate onto the piles, and then restricted access, which are any of the above that have to fit in a small space. Piling includes CFA and CHD. Machines for those are quite large, as you'd expect, the sort of excavator size, 100-ton plus. But we don't actually do CHD in restricted access. CFA, continual flight auger, we do. So that's where we are around the country. Pick a spot closest to you and see how the local area offices can help you is what I would say there. I've got a roving role nationally, so my name might pop up here and there. I'm currently based in the Northwest office, although I do spend some time in our head office, which is in the middle of the country in Burton-on-Trent, which is, for those geographically challenged, Derby, around there. So what are CFA piles? Well, CFA piles have been around quite a while, since 1980, mid-80s, I suppose. Funny enough, I was with cementation when they'd just been doing them for a few years. They were the main exponents of it at the time. Drill a hole in the ground with a continuous auger, and then straight pull that out, removing the soil as you go, filling the void with concrete. So it forms a straight columnar pile. The idea, if you're doing a job properly, is that there is no void left in the actual difference between the head of the auger and the face of the concrete. You actually concrete underneath itself, so it's tremid in essence, and you form that anything. Well, the diameters that we do is anything from 700 millimeters down to 250, but down to 26 plus meters we can go. There are others who will offer you a bigger diameter should you need it. One of the major problems with it, though, as you see there, is that there is a rather large amount of spoil generated. So that's one of the downsides of it, especially when you're dealing with a contaminated site, or carbon footprinting is your key. It's quite versatile. It's probably one of the most flexible piling techniques that's out there. It's suitable for most soil types. There are 1 or 2 exceptions, but not many parts of the UK where that becomes apparent. It can cope with most loads, most forces and most requirements in terms of settlement. Therefore, it's useful in pretty much everything, from low-rise residential all the way up to high-rise. A lot of central London piles, for example, on the city are done using larger diameter CFA piles. CHD. CHD is an auger displacement mechanism. The CHD initials stand for Continuous Helical Displacement pile. Uses the same rig, very similar technique, but there's a few interesting little twists involved with it that have some significant advantages for us that we can exploit. You auger to the depth that you need from the geotechnical design. You form a central core, and as you back screw out, it forms into an outer helix. So you end up with a screw thread on the outside of the central column, all formed in situ. It rotates in one direction, extracts in a different direction. In essence, what the helix does is it pushes the material out laterally. So you end up with a very small amount of surface spoil to dispose of, and it leaves all of the ground that you're going through pretty much where it is. In terms of volume, you're talking about a small bucket load at the surface, and it's usually the piling platform that's actually forming most of that near surface expulsion. Reinforcement, same as you would do with the CFA pile, you insert that after the event, and obviously that's designed for whatever loading conditions that we think we need. So there's a sort of schematic. We've got some photos coming up, but there's a schematic of what CHD does. We do it in two different sizes, split by the physical size. So the inner and the outer. So inner core, outer flange, 300, 600 millimeters and 400, 700. Obviously, geotechnical design dictates the length, and then the structural design is based entirely on the core. Geotechnical design is based on the outer diameter. So as you can see, it's quite an efficient use of the concrete that you install, both in terms of time for installation and materials that you've got there. In broad terms, for the same load, you'd be looking at about a third pile length for a CHD pile compared to a CFA pile. Loads we can take quite significant. There's some serviceability states there up to 1200 kilonewtons or 2.4 meganewtons on the larger pile size, and depths with our current fleet we can go down to about 26 meter or thereabouts. So it caters for a good proportion of the demand that the current market requires. In terms of the interface with the rest of the structure, we prefer to go on a standard 3D layout based on a nominal diameter. Group effects, which is something we have to consider, how close the proximity of the pile is to in relation to its efficiency for load capability, is based on those sort of diameters. So you can say broadly it's an equivalent for the cap detailing to around a 450, 600 diameter CFA pile, something like that. So caps are pretty much comparable with what's out there. Again, it's designed to interface fairly well with standard design operations. So what ground conditions can we do? Well, pretty much most. The only ones, whoops, jumped ahead there. The only ones really we can't accommodate very well is it's not designed to go into rock. So it's not an end bearing onto rock pile, but frankly, we don't really need it to be. We can get most of the capacities we need before we get into rock. So we're dealing with shaft friction and end bearing in granular and cohesive material. And as I say, it's pretty efficient at doing that. It's much more efficient than a CFA or a border pile would be. So the rigs that we use are designed by ourselves. They're fully computerized in terms of installation. we realized pretty early on that when you're controlling concrete flow, the installation rate, the extraction rate and the rotation, you need 3 arms to do that. And there aren't that many 3-armed rig operators available at any one time. So computerization was the way to go. The rigs that we have are intentionally designed to do both pile types. So we can install CFA and CHD on the same visit in the same project, if that's what's required. And of course, it's all recorded in this case. We use the subcontractor Jon Ball's, their instrumentation for the purposes. So it's all recorded in real time for golden thread, whatever it needs to be. We've got the data. So history of CHD. CHD has been around for quite a while. It came about really because what we were trying to do was stick with our in situ systems, get something in terms of a benefit as you can with the driven pile. They're much more efficient than, say, a CFA pile because it's a displacement mechanism. And also what we're trying to do is sort of find a sweet spot between the two, whereby you can deal with higher loads, you can use in situ concrete, because there are some distinct advantages with that. You've got the flexibility of being able to design your cages accordingly, and also you get the enhanced benefit of the displacement, both in terms of leaving muck where it is if it's contaminated, and with the efficient use of efficient use of concrete, a lower carbon profile that results. So the initial auger displacement techniques were developed back in the 1960s by some Belgian guys, and was used quite successfully on the continent through to the early 90s. There was a bit of a flurry in the UK market where various people introduced displacement auger systems, some of which are still available. But we really started work on ours in about 96. And then we've been offering it commercially since the early or late 1998 it was. I remember it well, but there's another story there. And we've been offering it ever since, both in the UK and various times across the world when we were working abroad. So, as I've said before, CHD is really, really efficient at load bearing. Broadly speaking, you can get a pile that's about 2/3 the length to do the same capability, same capacity that we dealt with before. We've been using it for a significant amount of time. I mentioned the papers, we'll come to those in a short while. Settlements, we haven't discussed that before, but settlements are the same as you'd get with CFA. Some cases slightly less in SLS, you'll get less settlement. And due to the piles being shorter, we save both in terms of time and materials, so much more efficient for both of those. Carbon emissions, we've done the sums, we've done the analysis, and like for like, it's way more efficient, even more so if you consider the carbon cost and material cost of muck away and what you're going to do with that. So it's quite a powerful technique, and one we think is really useful in the vast majority of circumstances where you get a CFA. Then this will be a technique that we can use. So, case studies. Oh, there's an aside. Just so you can sort of appreciate what the pile looks like, the photo you're seeing on the right-hand side there is an actual in situ CHD pile exposed. This was in a job down in over-consolidated clay in North London, and you can see there the central core with the flight cast, and obviously the reinforcement sits in that central core. It would be very difficult to get any reinforcement in that outer flight. So case studies then. This was a recent case study we finished last year, I think it was, in Union Park in Hayes for our client suite projects and the end client ARC, £8.5 million project. Data centers, what we were doing here. Overall costs about 600 million for several data centers on the site. Heavy emphasis on sustainability. and there's also a renewable energy plant on site as well. Perfect fit for what we were doing in terms of CHD, both in terms of the savings on carbon footprint from low carbon concrete, and also less consumption of concrete. So there's a definite benefit for them as they saw it for what we were offering. Ground conditions, London clay, about 2,500–3,000 piles in the end. We think we did there, both sizes. Loads up to 2,500 kilonewtons, a little bit of shear, and down to about sort of 23-ish meters, something like that. So a decent sized project for us there. Obviously, one of the limitations that we have with CHD is that the reinforcement sits in the central core. So we are somewhat limited in terms of the amount of shear that they can accommodate, the moment that they can accommodate. But there's usually a way we can deal with it by putting multiple piles in, sharing it across those piles, or some other dialogue that needs to be had. So we can deal with most circumstances with that, although that is a little bit of a limitation that we have. So environmental impact, bit of an example there for you. So we're looking at about 10 cubic meters of CO2 per pile for the piles that we were looking at putting in. CHD, we think it was about 4.4 cube per pile, so a significant saving. So in total, we saved about 16,000 cubic meters of CO2 for the same load bearing, same capability on the same site, which saved about 3,600 tons of CO2. In addition to that, we saved about 33,000 tons of waste spoil that would have done had we have gone with a project on CFA piles. So a fairly powerful argument there to convert from CFA to CHD, and in essence that's what we did for the 5 data centers and 2 energy centers that have so far been installed on the site, and who knows, we may be back in there to finish off the site later on this year. Oop. I seem to have frozen a little bit there. That's a bit disappointing. Let me try again. Oh, there we go. Apologies if this spins ahead about 3 slides. Again, summing up the ground conditions, see the boreholes there. One of the other things that we had to deal with, I haven't mentioned before, is that had we have gone into the depths we needed to, then we would have struck a Thames water asset, which obviously is best avoided if you can, especially as the near surface stuff had some significant nasties in it. And although it wouldn't have ended up as a pathway using CFA piles, it's obviously best to avoid it if you can. So that's what we did. There we go. Okay, so what we're seeing here is a plot that shows the ultimate capacity of the piles versus the depth at which we'd have to install. And as you can see there, got 2 graphs or 2 lines. We've got CFA and CHD. Note that the CFA pile 600 mil diameter is 26 meters long, and the CHD is only 17.5. And you can see there that in terms of the load bearing potential, they are pretty bob on, pretty close. You might consider that actually where you've got the loads up to about 3,000, then CHD is the way forward, which is the conclusion we came to. In terms of load tests, so they were looking here at how much a pile moves when it's under load. So this is the building performance, making sure the building doesn't settle too much. You can see there that certainly up to about 3,000 kilonewtons and beyond, the settlement of the piles is consistent between the 2 methods. So why would you not go down a method that takes less time to install, uses less materials, and is much more efficient? Bit of a no-brainer really when you look at it. Now, although these results are for clay, the same also applies for other ground conditions too. Another example. So this was for Morgan Sindall. We were looking at, again, 600 diameter CFA, and we looked at those ground conditions. And in this case, we could halve the pile length by going in on CHD. We also changed the concrete mix were able to do that, and went in with a very high percentage of GGBS, ground granulated blast furnace slag, to produce a very low and ultra low carbon cement, with 70% of it going that way, which saved an immense amount of CO2 for the project. So again, another driver for Morgan and Sindel as to why we could do that. And then obviously the traditional benefits of it being shorter and relatively speaking, less time on site to do the works. Same rig for both, so same preparation. So if we had have needed to go in with any CFAs, as I've said before, it's easy to do that. So information shared in another way. This gives you the split in terms of and comparison to a CFA job, what we've done in terms of carbon footprint saving for concrete, and also carbon saving for method 2. You can see there that the vast majority of it is, in this particular case for a job up in Glasgow, was done in terms of the material benefits to be had. So the change in concrete combined with the change in length. Another job, Oakland Homes this time, a residential site, former gasworks, lots of contamination. So wanted to leave that lovely stuff where it was. Again, carbon savings to be had, fairly consistent with that, and CHD piles there without moving the muck around site, leaving it in situ, which is obviously a preference where we can. Arundel, different job again, looking at CFA piles and CHD piles. You can see that overall the CO2 emissions were about 310, whereas CHD was about 160 per pile. Some details there in terms of the relative lengths of the piles. The other interesting one there, which I don't think we've highlighted very well before, is that the project duration. So whereas we thought that the CFA piles would take us 17 days to install, we were looking at 12 days for CHD. Just about 1,000 cube of material to remove from site from CFA. Nothing from CHD, was all dealt with on site, literally spread around where it needed to be. And obviously length savings, you can pick up on that too. So in terms of summary, I suppose, really, what can we do with the CFA pile? Well, CFA piles we do from 300 to 750 millimeters diameter, load capacity from 9/10 of nothing up to 3,500, and ranging in length from 4 meters to 26 meters, something like that. By comparison, CHD, we're looking around the same bottom end, obviously, up to about 1,500. We've done some tests in some ground conditions where we can go, in certain cases, up to about 2,500, as you previously saw. But the norm is about 1,500 for a pile capacity for a CHD, and lengths are comparable because the rigs are comparable. Just as an aside, on the left-hand side there, you can see sort of a grey thing. That's actually the tool that does the work for us. The mandrel is a straight-sided shaft that drives it. You can see that in the other two photographs. And you rotate that in the ground. That flight digs in, pulls the auger or the mandrel down. And as it does so, then it gets to the design depth. We then extract by contra-rotating, and that flight then forms the dual action of not just screwing it into the ground, but back screwing it back out and allowing the concrete to form into the void. So the idea is it's bottom feed, meaning the concrete comes out at the bottom and the concrete rises up and fills that void left by that helix. It works every time. Now we keep the concrete level, I would argue, pretty much between the two flight or two parts of the same flight that you can see there in that photo on the left. Okay. So, spun a bit ahead of time, really, but in terms of where we are, validated research. So this is the work we've done with various universities around the UK. And again, you can see the photo of the bullet that I pointed out before there. So looking at the embodied carbon, this is an exercise we did for the European Federation of Foundation Contractors Conference last year, published in their proceedings. And this was an exercise that was done in a site in, well, several sites actually, in Coventry and up in Scotland, where we did a comparison between CHD, CFA and driven sizes, loads, installation lengths and performance to see how they got on. We did it in both cohesive material, so clays, and then granular material, fine sands, silts and gravels. There are some limitations, as you'd expect for CFA and CHD, in terms of the sort of the levels you can get into a gravel. If they're very dense, you're going to struggle. And then because driven forms part of our core market, we've also done the same there. So we're looking at here the carbon consumption for the two areas. We've got on the left-hand side, we have the cohesive sites, and on the right-hand side, we've got the granular sites. The takeaway there is that the relative proportions of carbon consumption for each one is proportional in both. There's some slight advantages in the granular, but overall the proportions relative proportions one to another are pretty much the same throughout. But the takeaway I would suggest from that one is the orange, as I see it, the middle one, is obviously the CHD, and you can see that that is the lowest of all of the methods. Precast, although it's of a similar low, ultra low emission concrete, the transport costs and associated carbon footprinting of that transport movement to get the material to site, because it comes from a longer distance, sort of push that one up where it is. Obviously, if we're close to our plants, then there's something beneficial that we can do there. But as you can see, either which way you look at it, CH2 is the winner on that front from a carbon consumption. Bearing in mind this is for the same target load throughout. So in terms of what we've done, well, I've been involved with Dundee for several years. I'm slightly unusual in that I've got a visiting professorship with them at the moment, which is running for another 3 years tenure. That's how they work. In the past, so I do some research with a CHD in mind when I'm up there. We have, at the moment, we've got 2 postdoctorates, so that's 2 PhDs on CHD design and carbon footprinting that we've done, that are available in the public domain. There's at least 12 masters, depends on what gets picked up this year, and maybe more coming through. And so far, we've got over 16 peer-reviewed papers on design in terms of how you formulate the design. So it's a pretty copper-bottom design approach that we use. Those are in peer-reviewed papers like, if you've heard of them, Geotechnical, Canadian Journal of Geoscience, ICE, ground engineering, that kind of thing. And we've also been lucky enough to win 2 world-class awards for that research. The ICE Gold Medal, which is awarded by the Institute of Civil Engineers for the best published paper across all their journals in 1 year. And we won that last year, I think. No, year before now, year before. Obviously that's anybody from around the world could put into those journals for acceptance. And then prior to that, the previous year, we won the Specialist Geotechnical Research Medal from the ICE for other research work that we've done. We have ongoing partnerships, can't discuss those, but we have been involved previously with, obviously, my university, Dundee University, Durham, Southampton, and 1 or 2 others, which unfortunately I can't mention at this point in time. So we've got quite a bit of backup in terms of scientific information to detail what we do. So you don't have to take our word for it. It's all out there if you care to look for it, if that's your bag, and I may be able to help you out with those papers if you need anything from it. Okay, bit earlier than I planned to rush through that, and apologies for that. I haven't intentionally, because of that, I think I haven't dealt with any of your comments on the chat, so I'll have a look at those now and see if we can pick anything up. But thank you for listening. If you do have any comments, this is obviously recorded, will be sent out and put on YouTube, and my contact details are on there, so feel free to pick up whatever media mode, method or phone for the old school members that you might like, and I'll be more than happy to help you where I can. Thank you for listening, and we'll see what the questions are. If I don't manage to get through all of them, then I will pick up them after the event. So let's have a look and see if we can see where the chats go. Oh, there we go. Okay. Is there any comments or any questions anybody might have? I'd be happy to take them now. Well, I'll be very surprised if I've done that good a job for you, but hopefully, if anything comes up, you'll pop something over to us going forwards then, perhaps.
John, hi, it's Heather. There's no questions at the moment. You must have been very thorough. Oh. But if anyone has anything, still type it in the chat box and we will get a copy of it, and I'll pass everything on to John. Thanks.
Thank you for your time.